It's my pleasure to welcome Dr. Florent Heidet back to Berkeley. He was sitting back there a few years ago, pretty much at the same time when I was sitting there. So I was doing pretty much. We were doing pretty much what you guys are doing.
You was in the back, I was in the front.
Maybe that was correct. So after he graduated from Berkeley, he went to work for the Argonne National Laboratory, where he still is. He is a major international expert in fast reactor technologies, breed and burn technologies, but also molten salt reactors, and is also very active within the reactor physics division. He has many nice initiatives to promote young people within ANS and DOE in general. And I guess today is going to talk about fast reactors.
Yeah.
Welcome.
Thank you. Hi, good afternoon, everybody. Thanks for coming to this colloquium. Just like Max said, I was a student there like up until 2010, and I must say, I mean, if I'm successful today at Argonne, it's really thanks to the education you're getting from this department. So I'm really thank you to all the professors who were there when I was a student there. Like you guys are very lucky to benefit from it.
You're welcome.
I had to share an office with Max. So today I'm going to talk about FASTER. So FASTER is for FASt TEst Reactor. It's something that Argonne National Lab and some of the other national labs have been working on for the past year. So this is the outline of my presentation. I'll go through where it's coming from, and I'll discuss about how we designed this reactor. And then we look at the performance of reactor we are getting with it. We look at the core design, irradiation capability, safety aspect, schedule of deploying this reactor, etc. So it's a very long presentation. There's a lot of content to the presentation, so I'll try to skip through it relatively quickly, but at the end, if you have questions, please do not hesitate to ask me. This study was so we started with the ATDR study, which was Advanced Test and Demo Reactor study, which was starting in fiscal year 2016, so a bit more than a year and a half ago. The objective of this study was to look at, to define strategic objective for the country and to identify which reactor type would be the best suited to actually meet this objective. So three objectives were related to demonstration reactor, and the fourth objective was related to developing test capability in the US. So the FASTER reactor was one of the test reactor concepts which was developed as part of this study in order to inform all the metrics with respect to the test reactor, but this was not the only one. Another one was developed by INL, Idaho National Lab, and it was based on high temperature reactor technology. So basically we had these two test reactor concepts, and we compared one against another using a set of metrics. I'm not going to talk too much about this study because I could spend an hour on it, but this was a major milestone for the DOE last year. And now there are still discussion on moving forward with the finding of this study. So for the sake of designing the FAST TEst Reactor for this study, we wanted to design it as being passively safe, to be sodium cooled. Nothing said it needed to be sodium, it needed to be fast spectrum. And we wanted to use technology which was well established so that we have confidence we can deploy this reactor relatively quickly. So don't expect to see a lot of innovation in this reactor. This was not the purpose of it. The purpose of it was not to advance fast reactor. The purpose of it was to provide test and irradiation capabilities. And to that purpose, there was a number of desired features, and by desired features I mean if you wanted to score very well as part of this study, you had to meet certain criteria, such as fast flux level needed to be 5×10⁵ or higher. Thermal flux level needed to be that many. The test location we needed to have at least 24, etc. If we wanted to go after the highest score. But for instance, the HTGR, which was developed as the alternative test reactor, could not meet all those requirements. So don't think it was just okay. I want to meet this requirement and I can get there. But we did the best we could with the FAST TEst Reactor. So this is a team who worked on this concept for almost a year. So this is me. I led the core design for this reactor, and there were a bunch of other people at Argonne Only Steve Hayes was from INL, and he was our expert on the fuel, on metallic fuel, because INL was the only lab who manufactured metallic fuel, so they are still the experts on metallic fuel. So this is not just my effort, this is not just my work, it's a team effort. So this is an overview of the characteristic of the reactor. I'll provide a core layout and different view of the plant later on, but this is just to get an idea of what we're going to look at. So this is a 300 megawatt thermal reactor. It's converting, so as a test reactor, you don't need to produce electricity, because the purpose is just to provide test capability. But in order to recover some of your operating costs, if you can produce electricity and sell it, it makes more sense. But the trade-off with that is, you also have to pay for the steam plant if you want to do it. So there are pros and cons, but we decided to design it as producing electricity. Sodium cooled, it's a pool type reactor. We're using the ternary uranium, plutonium, zirconium metal fuel. Cladding and structural material is HT9, so this is a stainless steel which is typically used in fast reactors. Average burnup for a fast reactor is very low, it's only around 3.5%. The peak burnup is less than 5%. So the peak burnup is lower than the average burnup you get in the PWR. The purpose of this machine was not to get a good fuel utilization. The purpose of this machine was to be compact, to be cost competitive, and to offer very high performance in terms of irradiation capabilities. So there are a bunch of engineering features I will be mentioning as we go and we look at the different pictures. So let's start with the core design. So this part is the part I mostly worked on. So I'll provide some physics background just so that you understand where we came from and how we ended up with this core design. So first, our objective was to get high flux level. So you need to understand that the flux, the neutron flux, is almost directly proportional to the specific power of your core. Specific power is watts per gram of fuel. So there's no magic trick. If you want to have higher flux, you need to crank up this specific power. The second one, which is okay, but if you have very high specific power, like you are going to have very high temperatures in the fuel. So the peak fuel temperature is dependent on the specific power and the assembly design, mostly the pin diameter. But the peak cladding temperature is not dependent from the specific power. The peak temperature is just a condition of the coolant temperature mostly, within a few degrees. But some people tend to say, okay, the peak cladding temperature is proportional to your specific power. This is not the case. And then the pressure drop obviously is proportional to the specific power, not directly through the specific power. Just if you have more power, you need to push more coolant through the reactor, and if you do that, you're just increasing your pressure drop. So this is a simple story on where the process we followed to design the core. Starting point was we want a reactor that needs to be critical. If it's not critical, it's not going to be very helpful. And we want high flux for it. So to make the core critical, we want the smallest core, the most compact, so that we don't have an oversized plant which is going to cost too much money. So we are looking for the minimum size of the core, so the minimum height to diameter ratio that gives us a critical core. Once we have that, then we say, okay, it does not say what the power needs to be, so we crank up the power to the maximum, where we are very close from the thermal hydraulic constraint, and this is basically the maximum power, and therefore the maximum flux we can get from this design. So that's what we get. But if you just do that and you go with the minimum core size, the flux level you are achieving is nowhere close from 5 10 to the 15. It's more like 3 or 2 10 to the 15. So how do you get higher flux? So the objective is let's increase the flux level. So how do I do that? I need to increase the power density. That's what I just said before. It's very simple. Okay, so it's great. Okay, I increase my power density, but obviously now I'm exceeding my thermal hydraulics constraint. So I need to do something about that. So what I do, I reduce the height of the core. So I'm reducing my pressure drop, and I increase the diameter of the core to keep the core critical. It's great, but because initially in this step I had the the better configuration for the core. If I'm doing that, if I'm increasing the height of the diameter ratio of the core, then my core is becoming larger. So basically the volume is larger, but I have the same power. So it means I'm reducing my flux level because I increase the leakage probability. So then we need to keep going, and we say, okay, because we increase the core volume, we need to increase the power. Sorry, I went backward. So lower power density, I said that, and then we have to increase the total power of the core. So from this starting point, if you go with the minimum size of the core, to make it critical with the maximum power density, it's probably 200 megawatts. But because we had to go all those extra steps to crank up the power, we had to increase the power to 300 megawatts. Obviously, if we decide that the flux level is not very important, and all we want is, for instance, just the testing condition, the coolant, the environment, the temperature, then we don't need to go through all of that, and we can just stick with the simplest design. And there are a number of other, this is kind of a simplified description of the design process, but there are a number of other considerations which affect the core design. The number and position of the test location, obviously the more test location you have, the more neutrons streaming out of the core you have, so you're increasing your leakage, so same thing, it makes the core larger, or you need higher enrichment. Targeted fuel burnup, the higher the burnup, the more parasitic absorption you have in the reactor. And same thing for the reactivity control system, depending on the location, you can increase the leakage and the parasitic absorption. So these are the codes we use. Basically, these are the codes we have at Argonne and CMP6. Everybody has this one. Library are the same. The thermal hydraulics analysis was done with Super Energy 2/ANS. So this was a MIT code developed many years ago. Reactivity coefficients are done with percent. That's our perturbation code for FASt reactor, and SAS6, SAS4A, the code we're using typically for the transient analysis of FASt reactors. So let's take a look at the fuel. This is the only part of the faster reactor design which is slightly out of the ordinary. The purpose was to add as much fuel as possible in a given volume. So by doing that, we decided first to go to 6 weight % zirconium instead of the typical 10 weight % zirconium. And there are a number of studies which basically show that at 6% weight zirconium, all the characteristics of the metallic fuel remain the same. So there is no, and there are irradiation data actually for 6 weight %. We decided to use, we had the choice between LEU or plutonium as a fissile source. Truth being told, if you use LEU, your flux level is going to be 20% lower than if you use PU, no matter what. It's based in neutronics, it's just based on the cross-section and on the eta value. So obviously we decided to use plutonium, and because, plutonium is not enrichment, so we're not talking about enrichment when we're talking about plutonium. So in theory there is no this 20% enrichment limit, and we could go to 60%. But the issue with that is we did not have any irradiation data past 20%. So we decided to limit the plutonium content to 20% so that we have already experimental data, we can justify that the fuel is going to behave properly. Another change we did was metallic fuel swells a lot more than oxide fuel. So typically, we call the smear density, which is basically you leave some space between the pin and the cladding itself. So basically, this space is 33% of the fuel volume. But basically, it means we have 33% of empty space. And the burnup we are achieving in this case is relatively low, so the fuel is not going to swell as much as in a typical FASt reactor. So we decided to use 85% smear density instead of 75%. And because of the same low burnup, we decided that the fission gas plenum, which is typically at least the length of the fuel, will be shorter, so that we can have a more compact core and we can reduce the pressure drop. So now finally we can see what the core layout looks like. So it's somewhat unusual, as you can see. So all the blue region are the fuel assemblies. So dark blue and light blue are basically the same assemblies, same plutonium fraction, etc., but just different sets of cross-section for the neutronics. In light gray, you have the reflector. In dark gray, you have the shield. All the green location are the test location. The dark green are what we call closed loops, and I'll talk about it near the end of the presentation. And then we have these regions I will be talking about. And in pink, we have the reactivity control system. So you're probably wondering, it's weird, what is that? It says thermal test location, moderator, thermal closed loop. So because we do not want this test reactor just to provide fast testing capabilities, we want this reactor to be able to provide testing capability for light water reactor, MSRs, HCGRs, etc. What we can do with a FASt reactor, because the neutron leakage is so large, we can take advantage of the neutron leaking out of the core. We can moderate it with graphite, beryllium, zirconium hydride, something like that. and by doing that, we can enable thermal testing capabilities. So in that case, the brown moderator assemblies are made of beryllium can with zircaloy. But the specifics of this zone are still being refined. But the major issue with having that in a fast reactor is typically your fissile content in the fast reactor will be 20%. You have neutron leaking out, and the mean free path of fast neutron is 30 centimeters or more. The pitch of one assembly is 16 centimeters. So the mean free path of a neutron here is at least two assemblies. The neutrons are going to reach these regions. They are going to be moderated, and some of them are going to be reflected back towards the fuel. If you have a thermal neutron re-entering a region which contains fuel with 20% fissile content, you are going to have a very significant power peaking issue. And by very significant, I mean factor, peaking power factor 10, 20, 50. It's very like on the first few millimeters of the fuel is very, very significant. But the key is, like we designed this region, we verified that just with one row of reflector assembly, the thermal neutrons would be absorbed in iron. Because all this reflector assembly are made of Hg9, and iron is the main component of Hg9. And this was lucky enough to filter most of the thermal neutrons and preventing them from re-entering the fuel region. If it had not been sufficient to have just one row, we could either increase the density of the Hg9 in this reflector assemblies, or we could have two rows, but this would have been a major issue that need to be looked at. And then basically we have 4 test locations in the moderated region. So we already went through some of those characteristics. It's a 300 megawatt thermal reactor. The fissile content is nearly 20%. Active fuel height is 80 centimeters. That's a typical height for fast reactors. Beginning of cycle K effective is not very relevant. It's critical. So let's go to this one, the average power density and peak power density. So we see that the average power density is 560 watts per centimeter cube. To give you an idea, in a typical fast reactor, this value is 300. So basically, we crank up 75% more power than a typical reactor. And this is exactly why, instead of having a fast flux being 3 10 to the 15, it's like 5 10 to the 15, just because it's proportional to power density. And then what's very interesting and very important is the leakage probability. And I'll explain a bit later when I'm talking about the reactivity coefficient why it's so important. And these are the flux level we can achieve. So the target for the fast flux was 5.0 10 to the 15, so we were slightly above it. The target for the thermal flux was 1 10 to the 15 or above. And to give you an idea of what those values mean, so this is a fast reactor which provides some kind of thermal flux, but this thermal flux is higher than what you get in ATR, HFIR, like any reactor. This thermal flux is one of the highest you can find in the world. So, no, I think this was very interesting just to illustrate also that, in fast reactors you can actually achieve very significant thermal flux. It does not mean the spectrum in the thermal region are exactly the same as in a thermal reactor, but I have a figure about that later. So neutron thermalization, I'm going to go again very quickly over it. Neutron leaks out, they're being moderated. We decided to use beryllium. Initially, we looked at graphite because graphite is very cheap. First issue, graphite is not necessarily compatible with sodium, so you still need to can it with material to protect it. And the second thing is the slowing down power of graphite is not as good as beryllium, so you need a lot more graphite if you want to moderate neutron with graphite, which means your core diameter is going to be larger, and that's really something we do not want. So beryllium is obviously more expensive. It comes with a set of issues, but this is just one reactor, so we're not concerned about how much beryllium we need. But beryllium has the same issue as graphite. It needs to be canned into something to protect it from contact with sodium. So Hg9 would have been great, but Hg9, like we've seen, is going to absorb thermal neutrons, so it's not an option. And actually, this is exactly why in PWRs they do not use steel, because iron is not something they want. So in that case, that's exactly the same thing. So we decided to use zircaloy 2. And why zircaloy 2? Because this is the only zircaloy which has been tested with sodium. So there's nothing saying that the other zircaloy are not compatible with sodium, but we wanted to go with something we knew that it was going to be compatible with sodium. That being said, to be fair, it's not been tested at 700 degrees. So at high temperature, maybe this is not compatible, so more work and research needs to go into this aspect. So this is the power density distribution. As you can see, so this is basically where the thermal zone is. Obviously, there's no power in it because there are no fuel. There's no fuel. And as you can see, the thermal neutron will be wandering around there, and you see there's no peak power. The peak power is really located at the center of the fuel region. That's exactly what we wanted. This is the flux distribution. So in the light blue, at least on this part, this is the fast flux. On this part, this is the thermal flux. Between the red color and the blue color, there is a factor 5. So it gives you an idea of how far the fast flux extend and how far the thermal flux extend. So I mean, those values are the same I presented before, so nothing particular, but you can see the clear separation between the thermal flux region and the fast flux region. And if you're wondering what the shades are, they are simply the place where you have like control assemblies or test assemblies which are empty location. So obviously if you have no fuel in this location, you have a depression in your flux. So reactivity coefficient. Very short, we calculated the reactivity coefficient and they are all in line with what we're expecting for a fast reactor. With the exception of just one, which is probably the most important one, which is the sodium void works. So typically for a fast reactor, people are going to say, the sodium void works is positive, so it may be an issue, and this is true for large fast reactor. This is a relatively small one, very compact, and very high leakage. So basically what's happening is like when you're voiding the coolant from your reactor, you're hardening the spectrum, so you have an increase in reactivity. The compensating effect is that you're increasing the leakage because you're losing your coolant, so you have more streaming out of the reactor. But if you have a reactor which is designed with very low leakage probability initially, even if you increase this leakage probability by a factor 1.1, you don't see much increase. But in that case, we're losing almost 40% of the neutrons. So any increase in the leakage effect is very significant and results in a negative reactivity insertion, making it very safe. So the quasi-static reactivity balance, for people, probably most of you are not familiar with it, it's a very simple approach for fast reactor to verify that in case of accident, the typical accident considered for a fast reactor, the reactor is going to be inherently safe, meaning that the reactor is going to move to a direction where it's going to stabilize itself in safe conditions. And we have a set of 3 criteria to be met to meet these conditions. So those are the 3 criteria, and those are the value calculated for the faster design, and everything checked out. So this was very satisfactory. We are nowhere close from any of the limits. But that being said, it just means, after you go through your transient, you're in a safe state. It does not mean that during the transient you're not exceeding temperature and you're not melting everything. So don't take it, that's enough and everything is safe. It just means you're going to end up in a safe state if you did not melt anything before that. So that's our reactivity control was nothing particular there. Typical criteria for fast reactor, like we're assuming that one control rod is stuck, one is being inserted, so it's like all the control rods in one bank -1, and we want to make sure that just with all those rods -1, we can safely shut down the reactor. All the margin, I have on the next slide, are fine, that the shutdown margin, at beginning of cycle, end of cycle. If you're wondering why the end of cycle margin is much larger, or maybe why at beginning of cycle is lower, it's just because at the beginning of cycle you have excess reactivity because you have fresh fuel. So you have to compensate for the excess reactivity initially. At the end of the cycle you have no excess reactivity. So thermohydraulics consideration. In one of the first few slides I showed, the thermohydraulics was one of the design steps for this faster reactor. So what we do typically when we look at the thermal hydraulics for fast reactor, we look at the power generated in each of the assembly, including the reflector and the shield, because there is gamma energy deposition and neutron energy deposition in those assemblies. And we determine what the coolant flow rate required in each assembly to properly cool every assembly. So we do not want to have, and then we can adjust the flow in each assembly by having orifying plate at the bottom of the assembly. But we do not want every assembly to have a different size of orifying plate. Otherwise, managing the different assemblies is becoming very difficult because they will all be different. So we're trying to group assemblies having the same power together. So we have only a few groups. So we went through this design steps where you have to look, at how you group the assembly, or recalculate, the transfer of heat between the different assembly, and those are really the value we are interested in at the end of this analysis. So the peak coolant temperature, outlet coolant temperature is 550. The average is 510, so we're just 40 degrees above the average, so it's pretty good. The plant mid-wall temperature is 590. It's relatively high, especially for plutonium fuel. Typically, we like it to be 580 or below, but because we're cranking up 75% more power than in conventional fast reactor, that's still satisfactory. And the value by itself doesn't mean much. It's really during the transient, this value is going to go much higher, and we want to make sure there's no tectic reaction taking place. And the fuel centerline temperature, we just want to make sure the fuel doesn't melt. Typically doesn't happen unless you design the reactor with very thick pin in your assembly. So those are the different groups. We had 4 groups for the fuel. We had another 7 groups for the non-fuel assemblies. The design objective was to minimize the peak to sigma mid-wall temperature. So that's the 587 I mentioned on the previous slide. So now let's take a look at the plant layout, and then we'll jump into the safety analysis. This is what it looks like. So it's very busy. You have your core right there. You have your assemblies. You have the pump. One of the pumps, you see it there. You have the heat exchanger. So as you can see, like I said, it's a full type, so everything is filled with sodium. You have the instrument tree rotating above your assembly, so you can instrument all the test locations, so you can do all the measurements you may want. You have the fuel handling machine. So this one is slightly innovative. This was not one that was used in EBR2 or FFTF. This one was designed 10 years ago at Argonne for other reactor we worked on before. But it's never been used in an operating reactor to this point. And this is a cross-cut, and I will have a slightly zoomed-in cross-cut of the plant layout. So you have the 4 heat exchanger there. You have the 2 mechanical pumps on each side. Let's see what we have. We have the drags. So the system in black are basically finger going into the sodium pools. In case of accident, if you're losing your heat sink, you're still removing a fraction of the total power from the sodium. So this is a mechanism through which fast reactor can remove heat without having any circulation of sodium. And then we have the green line, which are basically the line going to the closed loops. And once again, I'll explain what closed loops are slightly later. And then let's take a look at the zoomed in one. So that's the same one. So you see the core shape. So it's been slightly rotated, compared to the figure I showed before. And we have the 3 fuel handling machine. So the question, why 3? If you go with one, it's going to be cheaper. Yeah, it's true. But the issue because of the closed loops. So closed loop basically have a tube coming out of them. So they prevent you from rotating the fuel handling machine above them. So this fuel handling machine needs to go around this one. And same thing for the instrument 3. We have 3 instrument trees, and the 3 of them are rotating in place during operation. So this is the position when we are refueling the reactor, where they are out of the way. And we have the in-vessel fuel storage. So the fuel, after it's been burned for a given amount of time, we take it out of the core, we put it there. We put fresh fuel assembly in the reactor. And after it stays in this position for a few years, we take it out, and then we can dispose of it, reuse it, or whatever else. So this is just the refueling position. So this is the reactor during refueling. So you have the 3 instrument trees I talked about. So they're out of the way. And during operation, as you can see, they're right above the core. So just to show that by rotating them, we are able to cover all the test locations except a few, which we decided not to, because we're not expecting that everybody will want instrumented test location. Some people just want to put a material there. They don't really care with the condition. They just want it to irradiate. So safety analysis. Let's see. So there were two objectives for the safety analysis. The first one was to verify that the drags, so direct. These are the fingers I talked about. Basically, the direct heat removal system were sized properly to remove enough heat from the sodium pool in case of accident. And then the second part was just to look at unprotected transient scenarios and make sure that the core does not exceed any condition. Unprotected means there is no scrum, there is no reaction from the operator, there is nothing happening. Something goes bad, nobody does anything about it. Let's see what happens. It's kind of the worst case scenario. If anything, any characteristic of the core is of normal condition, you will scram it, so it will not be such stringent scenario. So obviously the frequency of those events occurring is extremely low, especially because it assumes multiple failures of critical components. Safety analysis was performed with SAS6, SAS4A, that's typical code for, in the US at least, for safety analysis of fast reactors. So the margins are the following. We don't want sodium to boil, so this is sodium boiling point is calculated by SAS6. Fuel melting temperature is not calculated by SAS6, and this is depending on the composition of the fuel. So for uranium-based fuel, it's 50 degrees higher than this value, but for plutonium-based fuel, this is 1071 degrees Celsius. Reactor vessel integrity, so there are standards not to exceed, so this is ASME service level D. So that's the value provided for pool-type fast reactors. And then for the cladding, which is a major concern typically, we want to maintain a coolable fuel pin geometry. What does it mean? Basically, it means we are okay if we are melting the fuel near the center line. As long as the cladding retains its shape and we can have coolant flowing around it, it's fine. But if we have a breach of the cladding, or if we have relocation of the fuel within the pin, this is not a coolable geometry. Then we have this temperature at which we have a very rapid eutectic penetration between the fuel and the cladding. So basically, if the cladding reaches this temperature, you give it 5 seconds, you have no cladding anymore. So it's really very rapid reaction, maybe more than 5 seconds, maybe 30 seconds. It's very, very fast. You already have eutectic penetration once you're above 600 degrees Celsius, 650 degrees Celsius, but much, much lower. It would take you days for you to go through the cladding. So that's the 3 transient scenario we consider. Transient overpower, U top, so it's U is for unprotected, transient overpower, unprotected loss of heat sink, unprotected loss of flow. So those are the assumptions for the transient overpower. We're just assuming that we have control rod being removed fully by accident, an ejection of the control rod. So typically when we do the safety analysis, we are assuming like a withdrawal speed. So it's not like in a second it's being removed, so we're assuming it's removed by a few centimeters a second. And then we have the primary heat transfer system pump tripping, so basically not working. Intermediary heat transfer system pump tripping, which is 2K, and the feed water pump, so the feed water pump is for the steam plants. We are assuming, so the DH, so drugs or DHRS, same thing, different names. We have 3 of them in the pool, and we're assuming that only 2 of them are corrosional. Those things are passive features. So there's no reason that one of them will not work, but we're just assuming one is not working if for some reason the connection is broken or something like that. But this is not an active system. So each unit is supposed to be able to remove 0.25% of the total core power. 2 of them, that's only 0.5% of the total core power. So don't think that you're removing most of the power to the system. It's very minimal. And reactor, obviously, like I said, it's uncontrolled, so there's no scrum of the reactor. So the loss of flow results first. So those are the nominal temperature for the core, and this is what's going to happen, versus time. So time 0 is the onset of the accident scenario. So temperature goes up. As you can see, the fuel temperature is the one going the highest, and you have the peak coolant, you have the peak cladding, etc. Then it goes down, it goes back up, etc. And those are just dynamic effect of compensating, like the core is expanding, contracting, you have a loss of coolant, etc. And change in temperature, all of this effect takes different time to come into play. You have the vessel of the core is taken into consideration. You have the control rod drive line being withdrawn as the vessel is expanding. All of that is taken into consideration in SAS. So what we're really concerned about is the peak temperature. So those are the peak temperature we have. The cladding is quite high. It's 720, and we really do not want to exceed more than 710, 715. But it stays there for just a few seconds. And like I said, in order to see significant cladding damage, you will need to be above 7 and 10 degrees for several minutes or hours. So this is acceptable. All the other margins are fine. And basically, this point after a long time was what we calculated through the reactivity balance approach previously. But the reactivity balance does not give you this transient. So this is a good illustration of, at this point the temperatures are fine, but you need a full-blown study to make sure that during the entire transient you're not melting anything. So those results are for the loss of heat sink. So this is very straightforward. Everything goes up to the outlet temperature of 560 degrees. So there are no peaks or anything. So this is just the equivalent temperature. So all the temperatures are relatively low, especially compared to the previous accident scenario. And this is the third one we looked at. So this is a transient overpower. So basically you have an increase in power in the reactor. And as you can see, in this case, the fuel temperature goes very high. It's much higher than in the first scenario. But the cladding temperature does not go above 700 degrees. So cladding is fine, coolant is fine. Fuel is closing to 900 degrees, but we still have 182 degrees margin. And this is already, accounting, those are nominal temperatures, but these are nominal assuming like 2 sigma error on a number of factors. So we are very close from actually melting the fuel, very fast rate from melting the fuel. All right, so 2 more parts to cover. So this one is just about testing capabilities, and then I'll be talking about the closed loop so you get an idea what the closed loop looks like. So this is the core, like I mentioned, of the green, orange, and dark brown location are test location. We have 2 fast closed loops. We have 1 thermal closed loop. And all those other locations, we group them based on their location. So group A, for this one, are going to be the one near the core center. Group B are the one right against the fuel. Group C are the one further in the reflector region. A1 and A2 are the one in the thermal region, and B are the one in the thermal region, but further away from the core. That being said, those locations do not have to be this one. It's a fast reactor, so neutrons travel very far, and literally we can double the number of test locations. If we wanted in the reflector, it will make no difference on the core performance, safety analysis, or anything. We just arbitrarily took 33 locations just because we wanted to avoid contact with any of those, just to have more margin. But there's no reason that you could not have more or fewer test locations. Same thing, the moderated region does nothing for the core performance. So you could operate it just with reflector in this region, it would be the same. If you do not care for thermal testing capabilities, replace that with reflector assemblies and put more fast testing region in this area. Okay, so those are the flux level we are getting. And I've been talking a lot about flux, and having very high fluxes is nice, but if you have your peak flux on a very, very small volume, you're not going to radiate anything. It's not going to be very useful. So what we have in this table is like we multiply the fast flux by the volume of the test region, which is give you basically at the same time the flux level and give you credit for the volume of the region. So you can see that this value obviously in the group A, which are like at the core center, is like relatively high, and as you move further away, those are significantly reduced. In particular, if you look at the group C, it's reduced by a factor almost 5. So group C are this one. So the flux, so the volume is the same in all those test locations because they're the same assembly. So the flux in those regions is 5 times lower than the flux in this region. So it's not bad. If it was thermal flux, this would be like 20 times lower. So it's fast flux and neutrons travel very far. But obviously people will want to put their specimen near the core center because the damage accumulation will be so much faster. And we have the same table for the thermal spectrum region. But the difference between the different regions is not very significant. Like between the A1, A2, and B, it's just a few percent. But the closed loop is a factor 3 larger. And this is basically exactly what I said before. Is, if it was thermal region, this is a thermal region. So you have a flux at this point, and to assembly further down the line, you have a reduction of a factor 3. While for the fast flux, you needed basically 6 or 7 assemblies to see the same reduction in flux level. I already covered this one. So those are just as illustration. The spectrum you have is a different region. So blue and purple cannot differentiate really, but you can see in the FASt region the spectrum are relatively similar, and you can see that in the thermal region, yeah, you really have a carbon flux spectrum. So because of the beryllium, you don't have the bump you typically see in the PWRs, but that's what you get with beryllium. So now the last part, the closed loops. So the closed loops, it's nothing new. It was developed for FFTF many years ago. They've never been loaded in the core itself, but the FFTF reactor, it's a fast flux test facility, was designed with being able to incorporate 4 closed loop in the design. And the closed loop is basically a closed system. It's basically a loop that goes in the reactor, goes out. And the coolant you have in the loop does not need to be sodium. It could be anything you want. And the issue with that is if it's a different coolant, you need a different system to pump it, to remove the heat, etc. So it's becoming a very significant machinery. And this is what modules for FFTF looks like. So you do not put that in the core, you put that in the vessel, or in the building next to the vessel. So you can see the side of a door, that's the module, and the module goes up straight. So like right now it's on the side. But that gives you an idea of the size. And those modules were actually not for different coolants, they were actually for sodium. But because of these modules, the big advantage of it is that you could actually design experiments in which you're melting your fuel on purpose. You can get to this point because it's a closed system, so you can remove it and you can do whatever you want, and it's not going to contaminate the rest of the reactor. And you could have molten salt, you could have helium, you could have lead, you could have any coolant you can imagine. Obviously, if you start putting water in the test location near the core center, your fast reactor is not going to be very happy because you're going to thermalize neutron. But for the location further away, especially in the thermal section, you could put water there is no issue. So this is where the module will be placed. So that's the reactor vessel, so they will be next to it. So you get we saw the line on the cross cut of the core, it's the closed loop location close to the module. And then you have the chimney outside to remove the heat from this module. So this is different from the main heat removal system for the reactor. That being said, it's possible to design the closed loop, but it comes at a very significant cost. Like for FFTF, each closed loop module costed $100 million. So if you put three of them in the concept, it's like $300 million. And it's a shame if it ends up like FFTF where they've not been used. $300 million for nothing, literally. But I mean, not nothing, because we learned a lot from the FFTF design, and basically we can replicate it. And why did we use 3? It was one of the criteria for the study that this reactor design was for. So a few more discussion, remarks, and then I'll be done and you can ask questions. The layout of the core is very unusual. It's not like a circular core like you see in most of the design. The reason for that was because we were trying to get this thermal zone closer from the core center, so we can get higher thermal flux. So obviously, it was not the least leaky core, so we could have made it more compact by making it circular. And in fact, actually, we could make it more compact, circular, and have thermal region all around the core. The reflector region, like I mentioned, you can increase it, reduce it if you want more or less testing locations. And the last thing is the closed loops right now are all at 120 degrees, which forces us to have 3 fuel handling machines, 3 instrument trees, etc. We could actually line them up so that we could get just 2 of those machines instead of 3, cutting a bit on the cost. So that's the schedule for this reactor. So obviously, as part of the study, we did economic analysis. This reactor with the heat conversion system with the closed loop, the 3 closed loop is supposed to cost $2.8 billion, licensing and everything included. And we believe we can, operate it in theory 13 years from now, assuming that there is no money limitation and there are no licensing trouble. So